Hey everyone, and welcome to this explainer. Today, we're going to unravel something really fascinating, the mathematics of uncertainty. We are going to build a communication signal totally from the ground up. We'll start with just a single, tiny, highly uncertain little bit, and we'll scale it all the way up to a massive, continuous stream of network data. We rely on random signal analysis literally every single day for our Wi-Fi, our cell networks, our AI models. But how do engineers actually tame all that physical chaos using probability theory? Well, let's find out.
Okay, let's dive into this. Before we can even look at a complex communication system, we have to ask the most fundamental question that drives all of random signal analysis. When a signal or a channel or even a receiver's decision is uncertain, what exactly is probability being assigned to? Are we assigning it to the physical voltage on the wire, the exact time of arrival, or maybe just the human belief about a bit? This is the core mystery we're going to solve today.
Here is our roadmap for today. Section 1, Anatomy of Engineering Uncertainty. 2, Taming the Infinite Noise. 3, The Rules of the Game. 4, Updating Engineering Beliefs. And finally, 5, Scaling to the Limit.
Section 1, Anatomy of Engineering Uncertainty, the single bit.
So everything begins with what mathematicians call the sample space, usually denoted by a capital S. Think of this as the foundational boundary of what can actually happen in our experiment. It's like drawing a rigid box around reality. For this space to work properly, the outcomes inside it must be mutually exclusive, meaning, they can't happen at the exact same time, and they have to be collectively exhaustive, meaning absolutely every possible outcome is accounted for. But pay close attention to that last part, at a chosen modeling resolution. Probability isn't reality. It's just a structured mathematical description of uncertainty at a specific chosen level of detail.
Let's apply this directly to our anchor example for today. If our experiment is just observing a transmitted bit arriving at a receiver, our chosen modeling resolution is purely digital. Therefore, our sample space S is simply a 0 or a 1. That's it. Nothing else can happen in this specific model. It's a beautifully simple, discrete space.
Section 2, Taming the Infinite Noise, when sets aren't enough.
And this brilliantly illustrates our next problem. While a discrete 0 or 1 is easy to model, the physical world outside that model definitely is not. Our poor little bit is constantly being attacked by continuous thermal noise. To handle that infinite space safely, mathematicians built a very explicit pipeline. We don't just jump straight into assigning probability. First, we start with step 1, our raw set of outcomes. Then, step 2, we upgrade it to a topological space. This adds geometric structure, letting us talk about intervals and continuous ranges. Finally, step 3, we transition to a measurable space using something called a sigma field. We stack these mathematical concepts incredibly carefully so our engineering models don't just break.
Now, you might be wondering, why do we need that whole complicated pipeline? Well, comparing our discrete bit to continuous noise reveals a massive trap. Assigning probabilities to just a 0 or a 1 is totally safe. But noise voltage, that's a continuous value bouncing around on the infinite real number line. And out there on the infinite real line, there are extremely irregular, totally pathological subsets. If we just blindly allowed any random grouping of numbers to be considered an event, we could create subsets so weird that it would literally be mathematically impossible to assign a consistent probability to them. To fix this, engineers use a protective shield called the Borel field. Think of the Borel field as a super strict VIP list of valid events. It takes the topology, like intervals of noise voltage, say between 1.5 and 2.0 volts, and safely turns them into mathematically stable events. Thanks to the Borel field, an engineer can confidently ask, what is the probability this noise voltage corrupts my bit, without accidentally violating the fundamental laws of mathematics? It's an absolute game changer. Section 3, The Rules of the Game. Defining the measure.
All right, so we've got our safe spaces defined. Now we need the rules. These are the Kolmogorov axioms. They are surprisingly simple, but they govern the whole shebang. First, non-negativity. Probability is always 0 or greater. You can't have a negative 10% chance of a bit error, right? Second, normalization. The total probability of our entire sample space must equal exactly 1, 100%. And third, countable additivity. If you have mutually exclusive events, you can just cleanly add their probabilities together. These three little rules are the actual engine that lets us assign hard numbers to our bit errors and our noise models.
Now, what's really interesting about this slide is what happens when we ignore those careful definitions we just set up. We get Bertrand's paradox. If you ask for the probability of a random chord on a circle being a certain length, you actually get three totally different yet mathematically valid answers: 1/3, 1/2, or 1/4. How is that possible? Because the word random is completely meaningless without a specific mechanism.
This brings us to a massively important engineering takeaway. A sample space must describe the actual randomization procedure, not just the final object you're looking at. When an engineer is designing a communication network and they just vaguely say, oh, assume random fading or assume random noise, without defining the specific statistical mechanism, well, just like that circle problem, they are building a broken model. The system has to be fully specified.
Section 4. Updating engineering beliefs. The receiver in action.
So the rules are set, but what happens when the chaotic, noisy signal actually arrives at our antenna? The answer is Bayes' theorem. You've probably seen this famous equation before, but in random signal analysis, it's not just some abstract formula. It is the ultimate mathematical engine of decision-making for our digital receiver. It's a strict, logical rule for updating rational belief the exact moment new physical evidence arrives. Let's bring back our anchor example, that single transmitted bit. Before the receiver gets anything at all, it has a prior belief. Let's say there's a 40% chance that a 1 was sent, maybe based on historical network traffic. But then, boom, a signal arrives. It's heavily corrupted by continuous noise, but the hardware registers it as a high voltage. Bayes' theorem allows the receiver to instantly calculate the posterior belief. It updates that initial 40% chance to a much more accurate percentage now that the high voltage evidence has been processed.
Now, as we process all these different events, we really need to understand independence. Independence means that knowing one event occurred does absolutely nothing to change the probability of the other one occurring. It is a mathematical property of the product rule. Actually, a massive pitfall for folks is confusing this with mutual exclusivity. Remember, mutually exclusive means two things cannot happen at the same time. Independence means they just don't care about each other at all. They are entirely different concepts, and mixing them up will ruin a system design.
Let's move to Section 5 and see how this all builds together. Scaling to the limit, from bits to data streams.
Watch how we can scale this uncertainty across a massive timeline. At a tiny resolution of 1 microsecond, we're looking at a single bit error. That's just a simple Bernoulli trial, a success or a failure. But let's zoom out to 1 millisecond. Now we're looking at errors across a whole block of data, which requires the binomial formula to count up all those multiple trials. Now zoom out again to 1 full second of data traffic. We're suddenly dealing with a massive stream of millions of bits, where errors are individually super rare, but collectively, over time, they inevitably happen. This is where we reach the Poisson limit.
The Poisson limit is seriously an engineering masterpiece. It's the ultimate mathematical tool for modeling rare events in endless streams. When you have a staggering number of trials, like imagine millions of packets flying through a router every second, but the chance of any single packet dropping is incredibly tiny, the Poisson distribution swoops in to save the day. It perfectly models this chaos, giving us finite, manageable expected totals out of near-infinite data streams.
So the crucial point is this. Independence in disjoint time intervals isn't just some automatic assumption you get for free. Look at it this way. If I have a finite block of data with exactly 10 errors, and 8 happen in the first half, well, only 2 can possibly happen in the second half. They compete. That means they are dependent. But in the massive, infinite Poisson limit, the total population grows so incredibly huge that this competition just completely disappears. The fact that error counts in different time blocks become truly independent is actually a magical property that emerges from this rare event limit.
And there we go. We've built the signal chain from a single bit's sample space, protected it from infinite noise, defined the rules, updated our beliefs, and scaled it all the way up to a massive Poisson data stream. But remember what we established right at the very beginning. A probability model is not reality itself. It is merely a structured description at a chosen resolution. So I'll leave you with this to ponder. As we build communication networks and AI clusters of mind-boggling complexity, what happens to those systems when our chosen mathematical modeling resolution fails to capture the true underlying chaos of the physical world? Think about that and keep exploring. See you next time.